goal is just to look at it and say, what do I want? I want the equation to have a solution, right? That's what you want. Does it look like it usually will? Okay, so that depends on the assumptions that people make. Okay, so first of all, they define what a solution is. They say the solution is a differentiable vector function. Well, that makes sense. It better be differential because you're going to stick it in a derivative. So how could a solution not have a derivative if it solves a differential equation? Okay, it's a vector function, right? Because we have more than one equation, so we're looking for a function that looks like this, right? It's a vector, not a scalar. Okay, it's going to be defined on some interval containing the initial condition. So the idea here is that you can't usually request, because the system is nonlinear, I mentioned this last time, you can't request that the equation be solved everywhere. It's kind of like, remember when we talked about linear algebraic equations, we're like, when does the solution exist? And I gave you results that said, if you guess close enough to the solution, right? So it's the same kind of thing. It says, to have a solution here means you found a function that satisfies this equation, but it may not satisfy it everywhere. It'll satisfy it close to the initial guess. That's not the initial guess, that's the initial condition. You get the idea? Like, you can't guarantee that if you solve this equation, it's going to have a solution a long ways away from the initial condition, but to have a solution, it better contain the initial condition, right? So it's what we call a local result. All systems, when the equations are nonlinear, are local, just the way it is. Okay? So this, again, is just a definition of what we mean by a solution. Okay? All right. So where's the meat here? It says, okay, you want to solve this problem, you define the Jacobian, that's what I mean by a solution. Here's when it has a solution. It says, first of all, this function here has to be continuous. That's good. I mean, that's fine. Because if you write out a set of differential equations for a physical system, the right-hand side will be continuous. So it's not very restrictive, right? It says the Jacobian matrix, this guy here has to be continuous. Okay? It just means when you evaluate all these derivatives, that it has to be a continuous function of x and y. That's usually true too. Like if this function f is continuous, its derivatives will usually be continuous. Not always. Like I can find some pathological example to prove why you have to have this condition, but usually this should be okay. Okay? So the function's continuous, its derivatives are continuous, that all sounds good. Okay? Again, this will be local. Then it says this thing will have a unique solution on some interval containing that initial condition. In other words, everything's going to be fine. It's kind of like you tell you don't have kids, but when something's really complex and like something terrible happens in the world and they go, am I safe? You're like, of course. Okay. So it's the same kind of thing. Your kids, you're like, do I have a solution to this equation? I'm like, of course you do. Okay? Just relax. All right. So the conditions required to guarantee a solution for a differential equation are rather modest. They're actually more modest than the ones that are required to prove, like the algorithms we talk for algebraic equations. So, all right. So we're going to safely assume, although there are pathological examples, it's not true that a solution is going to exist to the problems we're talking about. Okay. So briefly, let's talk about this case. We're not going to go into any great detail. So this is the case where we have, so this is a set of linear differential equations, but the coefficients are not constant. You see this? So we have dy dx, we have a matrix A, but that matrix A might depend on x. If it depends on, it's still linear if it depends on x, but it's not as easy to work with as I'm about to show you. Okay? So set of differential equations with a matrix A that could depend on x, a set of initial conditions, so this is an initial value problem. Okay. We contrast initial value problem from something called a boundary value problem, which you guys have probably never seen before. But at the last lecture that I give in the class will be on something called boundary value problems, different than initial condition problems. Okay. That's where you have a spatial domain, and I might tell you one condition here and one condition at the other end. So, you know, it's a whole different ballgame. But most problems you've seen and we'll talk about are initial value problems. Okay, so we want to solve this problem. This problem is easier than the problem I just talked about, right? Because the problem I talked about, the right-hand side was some arbitrary function, nonlinear function f. Now this is a linear function, right? A could depend on x, but the right-hand side's linear in y. So it's simpler than the other problem. Okay, so the first thing just tells you when there's going to be a solution. And again, it's quite modest. I won't explain. in detail, but it builds on the case I just talked about. But it just basically says you want this thing to have a solution, then A better be a continuous function of x. Right? So obviously, you want to preclude things like this. It may seem all kind of mysterious, but like if you had a right-hand side of the equation that looked like this, I'll just write a single differential equation like this, right? You can see something really bad is going to happen at x equals 0 here. Okay? So what you're trying to preclude is that x equals 0 is of interest to you. So obviously, if I insist on this, I'm screwed. Like, right? I want to solve this differential equation. The initial value of x is 0. Well, the right-hand side's undefined. It's unbounded, right? So all we're trying to do with these conditions is preclude these kind of pathological weird things like this that happen. Okay? So what you're asking is the function a of x doesn't have things that look like that, 1 over x and evaluated x equals 0, stuff like that. Okay? If that's true, then this problem will have a solution, and the solution will be unique. It'll be local, but it'll be unique. All right. Now some of this should harken back to differential equations, but I don't know. So this should look, this example here, this is where we have right here, two equations, okay? Should look a lot like you guys did when you had a single second-order differential equation. Didn't you find two homogeneous solutions called y1 and y2 by getting something called like a characteristic polynomial and finding the roots, right? Those roots, by the way, are the eigenvalues of the matrix A. Same thing, which I'll talk about, okay? But anyway, let's say that you have you should have learned this in differential equations. Let's say I have a solution to that problem. I'm calling it y parenthesis 1 because I don't want you to think that means an index on which component of y I'm talking about. So y parenthesis 1 means a solution of that equation. It's a vector, right? If it's two-dimensional, it has two components. And let's say I have another solution called y parenthesis 2. So I found both these solutions. Then hopefully, because the equation is linear, this is why we love linearity. I can take the two solutions, multiply them by constants, add them together, and that's also a solution. That's called superposition. And that's why we love linear differential. We love linear everything, okay? But linear differential equations have this property. If you have two solutions, then the sum of the two solutions is a solution. That's not true if the system is nonlinear, but it is if it's linear, okay? All right. So, at some point you should say, you've never taught me how to solve a differential equation yet. I keep saying if you have these, right? At some point you should really call me on this and say, well, when are you going to give me one of those, right? But at this point, let's just say we have them. Add them together, there'll be a solution. If you have many solutions, like, right, if this is an n-dimensional problem and you have n y's and this matrix A is n by n, then you can find n solutions of these, and then this is the general solution. You know what a general solution for a differential equation is, right? You learned that? Okay. So for this system, where we assume we have n equations, that'll make this matrix A here an n by n matrix where the elements might depend on x. That's the general solution, right? It's just take all the individual solutions, multiply by constants, and add them together. I hope you learned in differential equations that if you want to find these constants, you have to apply the initial conditions. Did you learn that? Because right now you don't know what these constants are. But for example, in this case, you'd have two constants. You also have two initial conditions, one on the component y1 and one on the component y2. You apply those two conditions, you find the constants y1 and y2. OK. All right. So you see, I still haven't told you how to find y parenthesis 1 and y parenthesis 2. So I'm just going to continue. I'm going to teach you how to find them soon, but not yet. All right. So let's say you have a non-homogeneous problem. This should basically be all review. The only difference between what I'm talking about and what you've seen is I'm talking about systems of first-order equations, and I'm sure you talked about this in the context of a single second-order differential equation. But it should all look very familiar, right? You've got to find two solutions to this. The general solution is these times, each constant, add them up, find the constants by applying initial conditions, so on and so forth. Okay, if the problem is not homogeneous, like this thing here, okay, so g here, by being non-homogeneous, g can be a function of x, cannot be a function of y. If g is a function of y, the system is nonlinear. Okay, but it's a function of x, non-homogeneous, linear, set of differential equations. And now for a solution to exist, you need A and G both to be nice. These are very reasonable. Like it used to be just A had to be continuous, right, because we didn't have a function G. Now we introduce this function G because it's not homogeneous. Now G has to be continuous. Big deal. Very reasonable. Okay? All right, so this must either, you guys all take the same, you take in differential equations now, right? You take it from the math department, and you have a class that is just for engineering? Most of you? Okay. And you're using Kreizig's book, right? Same book? All right. Because it used to be that everyone took a different math class, and depending on who taught the math class, you might be an expert in differential equations, know enough to be dangerous, or know zero. Just depend on who taught the class. Like someone might spend the whole time proving when solutions exist and stuff like that. So someone's shaking their head like, that's what we're getting now. Sorry. We tried, you know. It's what happens when you have other departments teach service courses for your department, right? You have chemistry and physics and math, and you can't tell them what to teach. You need them, though, because we can't teach those. We can't teach 4 semesters of math. So the goal was to create that class with math so that they could focus on material that was, like, good for the engineers. So I don't know how successful it is. The good news is when you're seniors, we have this thing called the senior survey, and you can comment on how you enjoyed your 4 years. But until then, we're not so interested. Okay. Okay, good, you laughed. That was a joke, actually. Okay. All right, so you've seen this before, I know, that if you want to solve a non-homogeneous problem, the first thing you have to do is find the homogeneous solution, right? The homogeneous solution will look like in the previous page. You find y1 and y2, add them together, that's the homogeneous solution. Then you have to find a particular solution. Particular solution means a solution to the non-homogeneous problem, right? And you guys, I guess, learn different techniques to do that, I hope, in differential equations. I used to cover that, but I thought that's what you guys are supposed to be learning, differential equations, so I don't do it anymore, right? And you can do things like variation of parameters. I'm guessing you learned how to find particular solutions. You should have learned something like, if that solution looks like, if that g of x has a certain functional form, then you can guess what you think the solution for y might be based on what g looks like. Like if a g is an exponential, your guess of y is exponential. Like if g is a sine, I think you guess a cosine or some. Just ringing some bells, I hope. All right. I don't talk about that, but you can do it in the text. But so far, I've still not taught you how to solve any differential equations. So that's where we're going to stop. No, I'm just kidding. All right, so now I'm going to teach you how, and this is what you need for the homework. So you understand we're marching through the different levels of complexity. I said, first of all, if it's an arbitrary nonlinear function, all I did is tell you basically when a solution exists. I didn't even try to tell you how to find it or what it looked like. Then we went to the case where whoops. It looked like this, right? And then I said, oh, well, now I can at least tell you if you can find solutions, you can add them up and things like that, because it's linear and this was not. But I still didn't tell you how to find them, right? And then I went to this case and I said, well, now you got to find a particular solution added to the homogeneous of that's the solution without it. Yeah, okay. So finally, without further ado, as they say, now we'll go to this case. Okay, so this case is where this matrix A does not depend on x. Constant coefficients, it's called. Okay, and if that's the case, we can write it like this. Okay, and we're going to consider, we're not going to worry about the problem being non-homogeneous because it's non-homogeneous in the sense I talked about. You can make it homogeneous, like I showed you. Okay, so we want to solve this problem here. Okay. And I'm going to show you how to do it, and then I'm going to give you an example of how to do it. So it's an initial value problem. I'm going to give you the value of y at some value x naught. If this is time, it's usually 0. If it's a spatial domain, it means like one end of the domain or something like this. I'm going to give you the value of the vector y at that point, and I want you to find the solution of this set of equations. They're linear. They're coupled together. They have to be found simultaneously. Okay. Now we're going to come back. I taught you this before. And when we talked about eigenvalues, it was at the very end. So we're just going to review it. And so hopefully you remember this. But if not, I'm saying it again. Let's say this matrix A is guaranteed to be n by n, right? Because it maps y to the derivative of y. So it's definitely square. And so generally speaking, n by n. Let's assume that thing has n distinct eigenvalues, right? So you remember how to find the eigenvalues of the matrix A? So let's assume you found them and they're all distinct, meaning they're not repeated. No repeated eigenvalues at this point, okay? You know, if this is true, then the eigenvectors that correspond to those eigenvalues, which we call these the eigenvectors, those eigenvectors are linearly independent of each other. People are like, I don't remember anything you're saying. Well, go back and look at the notes, all right, because it's there. So if you have a matrix A like this, you can factor it, find eigenvalues and eigenvectors. If the eigenvalues are distinct, these eigenvectors are guaranteed to be linearly independent. Okay? So what's the implication of that? That means if you take these eigenvectors and put them in a matrix, which we talked about before, right, so this is all simple at this point. I get a matrix A. I do what we call an eigenvalue decomposition, or, you know, I find the eigenvalues. I find these guys here, n of them. Corresponding to those, I find these eigenvectors. Okay? Now I'm going to take these eigenvectors, each of which is a column, and I'm going to form a matrix by making these the columns of that matrix. Okay? That thing's called the modal matrix. We talked about that when I introduced it before. This matrix is guaranteed to be invertible because the columns are linearly independent. Okay? So that's why it's important. Okay. This is all review in principle. And then I taught you that the following was true. That if I took this matrix X I just formed here, it's an n by n invertible matrix, and I did the following. I multiplied on the left-hand side of A by X inverse and the right-hand side of A by X. That I would form a new matrix D. It's a special matrix in the sense it's diagonal, and along the diagonal are the eigenvalues. Okay? So this is guaranteed, as long as A has the properties I talked about. And when I talked about this, I showed you it was true for a simple example. It wasn't a proof, but it was a demonstration at least. Okay? So this is, it's not clear what this is useful for at this point, but it is true that if I take the matrix A, find eigenvalues and eigenvectors, plug the eigenvectors as columns in this matrix, do this transformation of the matrix A to a new matrix D, D will look like that. Okay? All right. And the value of this for solving differential equations is I'm going to be able to take a set of coupled differential equations and decouple them. So you see the problem with solving this differential equation, I hope this is true, right? If I give you this equation here, you know how to solve that, right? I hope and I pray that you know the following. Whoops. I don't know if you can easily read this, but so I've given you a differential equation. This is a constant coefficient A, that's y. The initial condition is y naught. The solution is y of x equal y naught e to the ax. Right? That's the most basic thing. How do you do that? You separate and integrate if you want to find that. All right? So you guys know how to solve that. Single differential equation, linear. Looks just like this, right? The difference is this is a set of differential equations. And you can't solve them one at a time because right? If you multiply a times y, you'll see the right-hand side depends on all the y's. You have to solve them all at once. You don't know how to solve them all at once. So when you're an engineer and you don't know how to do something, just you try to reduce it to something you do know how to do. Same thing you do in all of life, okay? Don't try new things. It's risky, all right? Do the same. Do what you know how to do and get really good at it. That's how you get rich and famous, all right? Renaissance man, I think not. All right, so my goal is to take this set of coupled differential equations for which in principle I don't know how to solve, and I want to transform it into a set of decoupled differential equations. They're all going to look like this. I know how to solve them all, okay? So that's what the value of this thing is, which I'm about to show you is. Okay, so let me draw a few things on the board to make this clear. In this class, you don't only learn about math, you learn about life, okay? Probably not what your parents want you to learn, though. He said something about giving up hope entirely. I'm not sure if that's what I want to do. Okay, so here's the problem we're talking about. This is what we want to solve, okay? We don't know how to solve it. So I'm going to use this transformation. I'm going to use this idea on the previous page. So I'm going to define a new variable called z, okay? Z is going to be this here, okay? So z is going to be defined as x inverse, right? X is that modal matrix thing. It's guaranteed to be invertible times y. Again, the way things work is someone first figured this out, and then they wrote it down, and now we can all pretend like we figured it out ourselves. But obviously, this isn't maybe self-evident. So that means if this is true, if z equals this times y, then obviously y equals x times z, right? This tells me how z depends on y. I can solve this equation for y. That's how it depends on z. All right. So this is convenient. And so what I'm going to do now is I'm going to rewrite this equation here in terms of z. Okay, so this is an equation in terms of y. I want to write it in terms of equation in terms of z. Okay, so this term here, dy dx, I'm going to substitute in this right here for y, right? X is a constant matrix. That should be a bold-faced z. Sorry about that. So I'm just taking this definition of y right there, and I'm plugging it into this derivative, and I'm going to plug it in for y right there. All right? So if I do that, I get the derivative of this right here, but x is a constant, so I can pull it out. That's where I get that term there. Okay? On the right-hand side, I have a times y, and there's y, so that's where I get ax times z. So I'm just doing a variable transformation. I assume you guys have seen this before. Just redefine my problem in terms of a new variable that I like better. Okay, so now this equation here that I've written right there, if I could circle it, is equivalent to this equation, just written in terms of z instead of y. So now what I'm going to do is I'm going to multiply both sides of the equation by x inverse. So if I multiply this by x inverse, I'll get x inverse times x. That's the identity matrix, also known as just the derivative, right? If you have I times the derivative, this derivative is just the derivative, okay? And then I have x inverse over here when I multiply by the left, so I get that thing there. That thing there, x inverse a times x, is what we call d on the previous page. It's, right, I told you, if I take this modal matrix and multiply on the left by x inverse and on the right by x, I'll get this diagonal matrix D with the eigenvalues along the diagonal. Okay? So this is, to me, this is great. I'm not sure how you feel about it, but I now have a set of differential equations, but all the differential equations are decoupled from each other. So for example, if you look at this first equation, it looks like, I'll write it out here. dz1 dx, right? That's the first element of this derivative right here. That's going to be that row times that column. Well, that's just going to be lambda 1 times z1. In other words, it doesn't depend on z2 or any of the other z. It's decoupled from all. It's a single differential equation and a single unknown. Just looks like the problem over there. Easy to solve. Same thing for the second equation, right? It looks like this. The one for z2 doesn't depend on z1 or any of the other z's. All right? So they all look like this thing here. Okay? So obviously, I've just done the first two equations. You can do it for any equation. That's what J is telling you which equation it is. Right? So it just depends on the eigenvalue for that equation and that z. So the solution looks like that. Okay. The question is, what is that thing? Well, that's the initial condition for the variable z. You don't have initial conditions for z. You have initial conditions for y. So if you want to apply this, you have to know what the initial condition for z is, and I found that here. Okay. So if you use this equation, this applies for any value of x, including x equals 0, which is written here. Okay. Right? And we know that y0 equals y0, so that means we can solve that equation for z0, which is the initial condition for z. Okay. So what I've taken the equation, I've transformed it into a set of equations for z. I have to do the same thing for the initial condition. That's all I'm saying. Okay? So this is great. I've solved all these equations. Now I know the solution, assuming I can compute this initial condition. Right, this is a vector. I just take the elements of the vector, and that's the solution of the individual equations. They look like this. They involve the eigenvalues. Okay? And so when you guys solve second-order differential equations, you probably call these things characteristic values or something. I don't know what you might have called them in your class. But if you had a second-order differential equation, you had two exponentials added together, right? Each of them had a different exponent. And that was roots of some second-order polynomial that you found. I don't know what you called those values. All right. So the only problem with this is you might have to look through this because there's a bit of math here. The problem is solution for z, not for y, right? And we want to solve the equation for y. So now we have to take the solution and convert it back. So a very common thing in math. Have a problem here, don't know how to solve it, convert it here, solve it, then convert it back to where you want. Okay, so now we have to convert the solution back to the solution for y. Okay? The good news is that I shouldn't say this, right? But all you're going to ultimately need is the bottom equation. People are like, okay, let me know when you get there then. But I'm just telling you where this comes from, okay? All right. So, so we have the solution for z, but we need the solution for y. And on the previous page, I told you y equals this capital X, the modal matrix, times z. So if I have the solution for z, I can construct the solution for y because I know the solution z and I know x. So I can perform this multiplication here, okay? And if you perform this multiplication, first of all, these columns, again, are the eigenvectors. It ends up looking like this, right? Because the first eigenvector, that first column, picks off the first value of z, z1. The second one picks off z2, okay? So the solution looks like that for y. And then I know the individual solutions for the y's, sorry, for the z's. And I'm just plugging them in there, right? That's the solution z1. It involves that thing times that. So I'm just plugging those in like that. Okay. So what did I do here? I found that as long as the equation has a set of, the matrix A has distinct eigenvalues, the solution will look something like this. But it's easier just to write it like this for reasons I'll explain, okay? The key thing is, what does the solution involve? It involves the first eigenvector times e to the first eigenvalue x. And then the same thing for second eigenvector, second eigenvalue, third all the way to the end. Okay? So all the terms involve an eigenvector times this, an eigenvector times an exponential term involving the corresponding eigenvalue. Okay? But it's, rather than explicitly compute these things at this point, I'll just call these things constants. I don't know what they are. And I'll find them by applying the initial conditions, as I'll show you in just a minute. Okay? So the idea is if you have a problem that looks like this, and it has distinct eigenvalues, then you're going to take this matrix A, find the eigenvalues and eigenvectors, and you can immediately write this as the solution. And now the problem's reduced to finding the C's. Okay? Because I just proved to you this is the solution. You don't have to prove that every time. You just have to use this equation. Okay. Oh, thank goodness. This is how life is. And when I was ahead of schedule, I could never use the entire class period. Now that I'm behind schedule, I keep getting further and further behind it. Just life, what can I say? All right, so let's see how we might use this. Here's a set of differential equations. This comes from a chemical reactor problem. It's not critical. So I think for this class, I may give you some models you don't fully understand on a homework or a test or something. All I'm asking you to do is just manipulate the equations, not understand where they come from. Like on the exam, I gave you, you may disagree, but I gave you a problem you should have been able to write the equations out for, because it wasn't like something you didn't know. Stoichiometry of reactions and things. But so, if you don't understand where these equations come from, it's okay. But it's two differential equations, one for a concentration. So there's the reaction scheme. Right? It's a sequential reaction. A produces B, and then B further reacts to produce Z. These reactions have rate constants called K1 and K2. You guys, I don't even know what you guys have covered. But you've seen rate constants and reaction rates somewhere, right? The rate constants of those two reactions are called K1 and K2. Concentrations, molar or mass, probably molar concentrations here, are Ca, Cb, and Cc. for this system, we only need to do two balances. We could either do A and B, A and C, B and C. We just do A and B, okay? And we get those two equations. So the idea here is that, you know, A is consumed by this reaction, and B is produced by the first reaction, but consumed by the second reaction. So that's why it looks like this. There's the initial conditions. We start by having all A and no B, right? And then we'll let the reaction take place. A will be depleted. B will probably build up for a while, and then B will start to be depleted as it goes to C. And by the time you're done, you'll have nothing but C. So maybe you should stop if you want B somewhere, okay? All right, so we have to solve this problem. And so what I'm going to do is, first of all, I'm going to define a vector which should be boldface. It's going to be CA and CB as the two dependent variables stacked on top of each other. And then I'm going to write this as a matrix. So I'm just going to take these coefficients and make them into a matrix A. So I've given you what the value of K1 and K2 is. So if you look at this equation, what is this row going to be? It's going to be minus K1. There is no CA term here, so it's going to be 0. And I told you K1 is 1. That's where I got minus 1 there. Okay. Same thing for this equation. Second row of this matrix is going to be K1 minus K2, right? Because that's the thing that multiplies CA, which is Y1, and that multiplies CB, which is Y2. I gave you that Y1 is 1 and K2 is minus 2, and that's where you get this. Okay? So there's your matrix A. Hopefully you realize this on the exam. This is a diagonal matrix. You can find the eigenvalues by inspection, right? So you don't have to work to find them. You can see the first those are the two eigenvalues, minus 1 and minus 2. Because it's not diagonal, it's lower triangular. Okay? And because at this point I'm assuming that we know how to calculate eigenvalues, I'm just telling you what they are. Obviously, if you were solving this problem, you would have to find the eigenvalues yourself. But I didn't want to do it. I didn't want to waste time showing it here. Okay, so that means if those are the two eigenvalues and those are the two eigenvectors, this is the solution right here. Okay? So maybe this helps you see what it actually looks like. So the solution is y, that's CA and CB, right, as a function of time. It has two terms. The first term involving first eigenvector and first eigenvalue, and second term, second eigenvector and second eigenvalue. Okay? And then I've just plugged in what is the first eigenvector and what is the first eigenvalue, and the same thing for the second eigenvector, second eigen. So it looks like that. So it's a vector equation, obviously. Okay? You don't know C1 and C2. So you have to find C1 and C2, and we've got 3 minutes to do it in this slide. So that's all I need. So you see at this point, if you're going to solve this problem, what do you have to do? First thing you have to do is form the matrix A. Once you find the matrix A, you need to find the eigenvalues and eigenvectors. Then you immediately know that's the solution. You don't need to do any of this derivation stuff that I did, right? Because I already did it for you. Okay? So once you know that this is the solution, now you have to evaluate the constants C1 and C2. That's why you have two initial conditions. Two initial conditions, two constants. Okay? You do it like this. So here's your equation for y. There's your solution. That's just rewritten from the previous page. I'm going to apply the initial conditions. So the initial conditions occur at t equals 0. Okay? So I substitute into this equation t equals 0. That just makes both these exponential terms 1, right? And that has to equal the initial condition. In other words, CA has to be 10, CB has to be 0. So that's an equation for C1 and C2. Now, being like I am, I'll solve this as a matrix problem, okay?